All right, there we go. That takes us to this point in the discussion. So now, here's the plan for today. We're going to be talking about the Michelson-Morley experiment. So a bit of a disclaimer. As per usual, I'm coming off of this mostly from memory, and so we'll go through the Michelson-Morley experiment, which was important in establishing a number of things, including special relativity, quantum mechanics. A variety of things went into. Thank you for that sub, King's Throne. I appreciate that very much. 43 months. That's almost 4 years. So this will be from my memory, talking about the Michelson-Morley experiment and the consequences of the Michelson-Morley experiment, like why it was interesting. As we go through this, we'll be relying heavily upon the source of all human knowledge, Wikipedia, or not the source, but the fountain of all human knowledge, Wikipedia, and in particular talking about how they put this thing together and why they put it together and so forth. This image shows the Michelson-Morley apparatus. So this was back in the day. They didn't have such amazing digital cameras like we have today. But this is the Michelson-Morley setup, and we'll go through the basics of the design. The Michelson-Morley experiment was specifically designed to detect the luminiferous ether. So back in the day, people were thinking, let's see how many times I can say back in the day in a single stream. That would be a great plan. People thought that in order to have light traveling from one place to another, because light is a wave, all waves must travel through some kind of medium. So water waves travel through water, sound waves travel through the air. And so light waves, because light had been demonstrated to be a wave, light waves must also pass through something. What are we going to call it? We need to come up with something that's really a fantastic name, and so they called it the luminiferous ether. Then the idea is, okay, here's the luminiferous ether out here out in space, and you have the sun, and you have the Earth going around the sun, and you have the Earth spinning on its axis as it goes around the sun. And the sun is moving around the galaxy, and the galaxy is moving towards the Great Attractor, towards Andromeda Galaxy, and together the both of us are moving towards the Great Attractor, and that's moving towards the Virgo cluster, or maybe the other way around, but the Virgo cluster is moving towards the Great Attractor. But anyways, let's make sure that I get that in the right order. We don't want to mess up the Great Attractor. Let's see, so the Great Attractor. Luminiferous ether, that's exactly what it is. So the Great Attractor is a region of space where things seem to be moving. Gravitational anomaly in intergalactic space, a apparent central gravitational point of the Laniakea supercluster, has a concentration of mass millions of times more massive than the Milky Way. However, it is inconveniently obscured by our own Milky Way that's in the galactic plane. All right, so let's see if I can find the velocity distribution of galaxies. As long as we're taking a tangent briefly from the Michelson-Morley experiment, I might as well try to pull up the velocity. Here we go. So this is showing the motion of the Milky Way galaxy and other galaxies in the direction of the Great Attractor. So that's the Great Attractor. So we're all drifting in that direction. So the Milky Way and the Andromeda Galaxy, we're falling towards the Great Attractor in the sky. And a bunch of other galaxies, clusters of galaxies, are moving in that direction. So the Laniakea, I'm not sure what that is, never used that in a sentence before. But there's always a first time, I suppose. So all that being said is that this luminiferous ether, the substance through which the light must travel, because light is a wave, that was demonstrated by the Young's double slit experiment, that you get the interference pattern from light. So light is a wave, therefore it must travel through some medium. That medium has a name. It's called the luminiferous ether. And because the Earth is going around the sun, spinning on its axis, orbiting around the Milky Way galaxy is moving towards the Andromeda Galaxy, which of course hadn't been known at that time. The Andromeda Galaxy wasn't really discovered as a galaxy, or like as a separate galaxy, until Hubble, which was, like 30 years after this, but that no matter. The point being that the ether is going to be there in its own state, and the Earth and the sun and the Milky Way are going to be moving through the ether. So even on a given day, so if we were to just look at a given day, what would happen is you have the luminous ether out here, and here is the Earth. At one point, the Earth is going to be moving at your laboratory in Chicago. is going to be moving in this direction, or it wasn't Chicago, it was Cleveland. The Earth will be moving in this direction, or your laboratory will be moving in this direction, and 12 hours later, your laboratory is going to be moving in this direction, which means that regardless of the motion, the ambient motion of the ether, maybe the ether is drifting in some particular direction because of reasons, that your laboratory on the Earth is going to be moving into and away from the ether wind at some point. You're going to have a difference in velocity of your laboratory relative to the ether of whatever the rotation rate of the Earth happens to be at your latitude. So you wouldn't want to do this at the North Pole, because you wouldn't see anything at the North Pole. You would see something over the course of a year, because the Earth would be drifting in its orbit around the sun, and you would get the difference in the orbital motion of the Earth around the sun. The orbital motion of the Earth around the sun is what, 30 kilometers per second? So that's 30 kilometers per second. 30. That's a 0. 30 compared to 300,000. Kilometers per second, so the 3's cancel, that's 10 out of 100, that's 10 out of 100,000, so that's 10 to the 1 out of 10 to the 5, 10 to the 1 out of 10 to the 5, that gives you, what, 0.0001, so 0.01%, so 0.01% would be the Earth's orbit around the sun from one point to the other. You get a factor of 2 there because you're moving in one direction and then you're moving in a completely opposite direction, as opposed to starting from 0 and then going around that. But the rotation of the Earth isn't quite that fast. We don't spin quite as fast as we orbit. We spin at 40,000 kilometers per hour around the equator, kilometers per 24 hours around the equator. So it's something, I don't know what it is. It's like 10 kilometers per second. Something like that, to get is roughly the rotation speed of the Earth. So are the quantum fields synonymous with the luminiferous ether? So the luminiferous ether, we will find out about the luminiferous ether as we go into this. So anyways, this is going to be the movement of the laboratory relative to the ether. So the ether is going to have its own motion, and we can't control that at all because it's its own thing. If it's there, it's its own thing. And so all we can measure is our motion relative to the ether. And it doesn't matter, which way it drifts, because ultimately it's the velocity of our laboratory at this point and at this point that's going to make the difference. So, because our laboratory is rotating around the axis of the Earth, and it's going to be moving in one direction, and 12 hours later it's going to be moving in exactly the opposite direction. And so in one case, light traveling in some direction is going to be going with the ether. It's going to be traveling with the ether and therefore be kind of pushed along with the ether. And when we're traveling in the opposite direction, the light's going to be going against the ether wind. And so it should have like a headwind and a tailwind. And so that should affect the speed of light in these two different directions. And that's what the Michelson-Morley experiment was designed to measure, is the speed of light in two perpendicular directions, or two different directions. And so not perpendicular, but anti-parallel directions. So as they measure the speed of light, they will be able to determine which way the ether wind is blowing relative to the Earth and how fast it's moving, and also demonstrate that it's there. And that's the main thing, is that if they see a signal that the speed of light is somehow different in one direction compared to a different direction, then they will be able to say, we can see that there is an ether and that it's moving in this direction relative to the Earth, and they'll be able to measure some of the properties of that ether by measuring the speed of light in these different directions. But you can't just make a measurement of the speed of light in one direction. What you need to do is you need to be able to measure it in two different directions and compare those different directions with each individual measurement that you make, both in this sense, when your lab is in this location and when your lab is in this location. So how does one set this up? Well, that requires the development of an object that can measure the speed of light, or in particular that can measure changes in the speed of light, and that's the important thing. And so this is where Michelson developed an interferometer. So a particular type of interferometer. So with this interferometer, what you do is you send light in one direction. So light comes in like this, and then you split that light into two different beams. You have one beam that goes through, so that you have a beam splitter right here. So that's a piece of glass that will split the beam into two different directions. It's partially reflective glass. It splits it into two different directions. Part of that beam reflects and goes in this direction. Part of the beam reflects or transmits and goes in the opposite direction. Then you put a mirror on the far side and a mirror over here. So light comes in, splits. Some of it goes down one arm. Some of it gets reflected down the other arm. This is called, I think this is called the longitudinal arm, and this is called the transverse arm. And then it reflects back off of that, recombines at the beam splitter, and comes out the other end. And then you put your detector right here. This is your detector. That says detector on it, even though it doesn't look like it says detector. Oh, I need to cross the T. There, detector. So you have your detector here. Light comes in, gets split. Part of it goes down one arm, part of it goes down the other arm. They recombine at the beam splitter, and then you can detect the combination at your detector. Now, in general, what you want to do is, if the lengths of the arm are exactly equal to each other, so if this length of the arm and this length of the arm are exactly equal to each other, then the number of wavelengths, so the light that you put in has some particular wavelength. If you put in a monochromatic beam, so you have like one specific color that you put in, the light comes in and it will move down here. You'll have some number of wavelengths of that light that come down one arm, and then it reflects, and you have, so you get the number of wavelengths back here. And then you can compare that to the number of wavelengths of light that you have going down the opposite arm. And so if you have an equal number of wavelengths in both of these arms, so say you have like 500 wavelengths here and 500 wavelengths here, then when the two beams recombine, they will recombine and they will be in phase with each other. So they'll be in phase with each other, which means that you get the sum back. You'll have this half of it will have a wave like this, the other half will have a wave that looks like this when it reaches the detector, and so when you add these together, you get a single high amplitude wave. If, on the other hand, this arm has 500 wavelengths and this one has 500 and a half wavelengths, then one beam is going to come back into the detector like that, and the other beam is going to come back into the detector like this, and when you add those together, you get nothing. These two things added together gives you something that adds coherently. These two things added together gives you something that adds destructively, or like constructively and destructively, and so there's no signal. When you're done with this experiment, or when you have the arm lengths that differ by half of a wavelength, then you get destructive interference like this, and you get what's called a dark fringe. Okay, so now it doesn't, when you have a monochromatic beam, meaning that you have a very specific wavelength of light coming through, one specific color, then it actually doesn't matter that it's 500 wavelengths and 500 and a half wavelengths, for example. You could have 500 wavelengths in one arm and you could have 300 wavelengths in the other arm. And as long as you have the same color going through, the same color light going through the entire apparatus, this will also combine with the two things in phase with each other. And so it's whether it's an integer or a half integer multiple of the wavelengths in both arms. And honestly, it could be 500 and a half, and this one could also be 500 and a half, and you would still get constructive interference. The point is that relative to each other, it's an integer. When you do the subtraction, it's an integer number of wavelengths that are in there to get constructive interference. If it's when you do the subtraction of these two numbers and you get a half integer number, like 3.5 or something like that, then they're going to add destructively. So that's the point. If the arm lengths are the same, you get constructive interference, or if the arm lengths are equal to each other down to a multiple of the wavelength that you put in, you get constructive interference. If they're half integer apart from each other, you get destructive interference. Now, that is for a monochromatic detector. And this is actually the design that's important for the development of the gravitational wave observatory like LIGO, because it's basically designed the same rough design of the experiment. There's some details in there that we will get into when we do a stream on LIGO. Now we're talking about Michelson-Morley. We wanted to do this one first because it sets the groundwork for later experiments that use interferometers. Now, this again is for a monochromatic beam where you have one single wavelength of light coming in and coming back out. What Michelson-Morley did is they designed their apparatus to be a white light interferometer. So white light interferometer. And there it actually does matter that it's the number of wavelengths. So they send light in, it goes through the different parts of the apparatus like this. And this, with a white light interferometer, you have to have exactly the same wavelength or the same length in this arm here as you do in this arm here. So the reason is that when you have white light, you have multiple wavelengths. You have every wavelength of light going through the system. And so if there's any discrepancy between one arm length and another, it's not whether it's a half integer multiple wavelengths or not. It's that any discrepancy between them will result in destructive interference at the end. So that's a significant difference between a regular interferometer and a white light interferometer, is that a regular interferometer is one where you choose a particular wavelength. You might put in green light, so you have a wavelength of 532, 500, that's a 5. 532 nanometers going in, for example, so that's green light. A green frequency double neodymium YAG laser will give you this wavelength of light. And so you have some number of wavelengths that fit in this arm and some number of wavelengths that fit in this arm. And as long as they're integer numbers, or the difference between them is an integer number, you'll get constructive interference coming out. However, when you have white light, you're going to have this light, you're going to have, every other wavelength that's in there, 600, 601 nanometers, and 601.00 something nanometers. So all of these wavelengths are going through the interferometer at the same time. And so if these arm lengths are different at all from each other, then one of these wavelengths of light is going to have destructive interference with its counterpart that goes through the other arm. So the white light interferometer, it forces you to have the same arm length in both directions in order to get the fringes to line up, in order to get the kind of pattern that you want to see in your detector over here. Now let me show you what that pattern looks like. Does it show up on this? It is not that. That is Einstein's equation. This is the picture that we already drew with the sun going around in the spring and the fall. It turns out they didn't need to do it. This is the original design of the Michelson interferometer. Okay, so he has a lamp right here. He's got the beam splitter. He's got these mirrors at the other ends. And then it comes back and here's his detector right there that you peer through with your eyeball like that. In looking at that detector, looking at the combination of the beam that comes back out. What we're actually looking for is not that. That's going to come up a little bit later. This is the fringe. This is the fringe pattern that you get. So in the center of this is when you have two arms of exactly equal length. The photons that go through and come back out right here, they combine, and notice that there's no color to the central peak, the central fringe right here. There's no color. That's when exactly the same number of it's exactly the same length going from one end to the other. You are going to have, because the beam spreads out, it's going to bounce off of different locations, and you're going to have things coming back from slightly different paths as it goes through there. And so you're going to get a series of fringes. You can see the series of fringes here. Let me show what the fringes look like for a monochromatic interferometer fringes. So interferometer fringes from a monochromatic beam are going to look like what? Let's see if I can see a good one. Like this, basically. Okay, so those are fringes from a monochromatic beam. Of course, this is a Mathematica notebook, so it looks like. Okay, here's interference fringes. Well, yay. Here's interference fringes from a monochromatic beam. This is coming from a different source, and so the fringes are shaped funny. But there you get really nice fringes that extend for a long distance, right? So each bright portion here, each bright fringe, that is where you get another wavelength of that same light. So this is probably around 700 nanometers because it's in the red. And so you have 700 nanometers, and then the path length difference is going to be another 700 nanometers gets you to the next fringe, and then the path length difference of another 700 nanometers gets you to the next fringe, and so forth. So all those fringes correspond to shifting the wavelengths by one crest or trough. When you have a white light interferometer, which is the one that we're talking about here, you'll notice that the colors blend out here. So, for example, with the blue, or I guess we'll use the red. So the red fringes are going to have some length, some separation between them that corresponds to whatever the wavelength of red light is. And the blue one's going to have a different fringe. So you'll notice here you have the white light fringe in the center, and then you have blue kind of in between in this first trough, and then more blue in the second trough, and then even more blue, and then it starts to blend together. So that just shows that if you have a separation from the fringe here that corresponds to some difference in the path length, that's going to cause a different interference pattern when you have for blue light than it does with red light. And so the colors start to appear because of this interference. So again, this is, you have light coming into your apparatus, you split the beam in two different directions, they recombine. Some of those paths are going to be bouncing in slightly different directions, and they're going to come back and they're going to recombine, and this is going to have a slightly different length than it does over here. And those paths that are off center that come back and recombine are going to cause interference. You're going to get destructive interference from all the different wavelengths. The amount of destructive interferenceness is actually going to depend on the wavelength. And so that's going to show up in this, where you get blue light interfering at different separations than red light. Okay, so that is an advantage of the white light interference pattern, is that for the Michelson-Morley experiment, is it allowed them to see the central fringe. Because you notice how blurry it gets. There's basically no fringes out here. You wouldn't necessarily even be able to resolve them. There's fringes in red, but the pattern is kind of washed out because the green light adds constructively here while the red light adds destructively at a given location, so it gets washed out. However, the central part, these dark parts, those are very, very prominent. And so instead of having an interference pattern for your experiment that looks like this, if you want to be able to see any drift in the interference pattern, you want to have something that basically looks like this. Okay, so you have very sharp edges to the interference pattern. That's the important thing here. You have where it combines constructively here, and then you get one destructive interference dark fringe right there, and then it's all essentially washed out over here. And so if there's any difference in the path length, or in particular, if there's any difference in the velocity of light as it travels down the two arms, which I just erased. So if the velocity of light is different as it travels down the two arms, then that's going to correspond to a different number of wavelengths that fit into the two different arms. And so that's going to show up as a change in that fringe pattern. And if the fringe pattern is very sharp edges, so you basically just look for this pair of dark lines. The way that they set it up in the Michelson interferometer, it was on a dark fringe, so it was actually dark in the center, and then you have two bright lines. But that makes it easy if you're using your eye to do this, because there weren't any digital cameras back then. So you're using your eye to do this. It makes it really easy to distinguish between things that are lined up and things that are not lined up. You can see very small changes in the distance because it turns into a fairly large change in the interference pattern. So that's what's important with this setup, is it's designed so that you can pick out these fringes and therefore tell the difference between the speed of light going down these two different arms. Why not use sodium lamp for narrowband? So the reason that they didn't use the sodium lamp is because the sodium lamp, if the arm length stretches by some amount, so say the arm length stretches by a wavelength, it will shift the fringe by one, and it's hard as an experimentalist, especially an experimentalist back in the day, to know that a fringe has gone by. These fringes can pass by very, very quickly. So now when we make these measurements with the interferometer, we have a computer sampling the camera and counting the fringes that go by, because a computer, you can process the image, you can say, oh, it went dark, now it's light again, now it's dark again, now it's light again. And so having a monochromatic beam means that you have many, many high quality fringes, and as they pass through each other, if they pass through quickly, you won't be able to count them. And so by going to a white light interferometer, it means that any displacement will blur the fringes completely. And so I guess that's an important point. So I'll remember to clip this and move it back in. Okay, that is the setup for the Michelson interferometer. Now, they tried it initially with this apparatus, an apparatus like this. This was in 1881, but this wasn't big enough. So it wasn't sensitive enough to see the effect that they wanted to see. So the way to make it bigger, like the way to make it even more sensitive, is to make the arms longer. Because again, you care about some number of wavelengths that fit into each arm, and if you want to make a precise measurement, let's say that you can make a measurement that is on the order of like 1 nanometer. That's supposed to be an N, 1 nanometer. So you have some small measurement that you can make, that you're capable of making with your apparatus. But what you want is a small fraction of the length. So if you can make a 1 nanometer measurement, but your apparatus is only 2 nanometers long, then that's only 50%. That's not very precise. So of course you're not going to make an interferometer that's 2 nanometers long, but we can pretend. So if you're only capable of making a 1 nanometer measurement and your instrument itself is only 2 nanometers long, then that's not going to cut it. That's a 50% uncertainty. And so what you do is you lengthen out these arms as much as possible, because then let's say that you have a 1 nanometer, precision, but you have a 1 meter arm, then that gives you a 10 to the minus 9, a precision of 10 to the minus 7%, like 10 to the minus 9. You get a measurement precision that looks like 0, 0, 0, 0, 0, with 8 zeros in front of it and then a 1. Okay, so that's why these interferometers have fairly long arms in this case. So this was when they first kind of set the apparatus up to see how it worked, but it still wasn't long enough to give them the precision that they needed. They couldn't do 1 nanometer length. They could do maybe 100 nanometers or something like that. And so they needed to make an interferometer with larger arms. The problem is interferometers with larger arms are hard to control. So if you have an interferometer that has, say, even 10 meter long arms, that's a big flimsy apparatus that you have spread out in your laboratory, and anything can shake it. So you have animals walking on the roof of the building. You have squirrels jumping off of trees and hitting things. You have birds flying into the windows. You have all sorts of problems, earthquakes. You've got waves crashing into the shore, because this was in Case Western Reserve universities where they ran this experiment, and so that's in Cleveland. And so you have waves from the lake smashing into the shore. And so all of these things are going to add noise, and if you have a big floppy system, then that noise is going to be exacerbated. People talking in the hallway or stepping with large footsteps on stuff is going to interfere with your measurement. And so what can you do to address this? Because not only do you have to have this apparatus, but you need to be able to move the apparatus, because the whole idea was that you have the Earth going around the sun, and so you want to make a measurement with the apparatus pointed one way, and then you want to rotate the apparatus so you can make a measurement of it pointed in the opposite way. Because, for example, suppose you have your apparatus set up, if you have your apparatus set up like this, okay, so there's your mirrors and here's your beam splitter, and if the ether wind is going like this, it's going to affect both arms exactly the same way. So if your ether wind, where the photons are supposed to be traveling through, is running at an unfortunate angle relative to your interferometer, you won't be able to see any effect. So what you need to be able to do is be able to rotate your apparatus and make a series of measurements at a particular time, so that you can, for example, so here, pretend the ether wind is moving like this. You can set it up so that your apparatus is like this, and then you can rotate your apparatus so that it's set up like this, and then you can even have it so that it's set up like that. So you can measure basically any effect that happens at any angle relative to the motion of your laboratory through space. Okay, just in case, because you don't know which direction the ether wind is blowing, and so you need to be able to find what it is by basically maximizing what is the difference in velocity that you measure. What is the difference in length versus the difference in velocity. They are related to each other, especially if there is an ether. So the velocity of light is different in one direction than another, and so it takes a different number of wavelengths to get through the system. And so you want to maximize that signal. You want to maximize the difference in fringe that you get from one orientation to another. And the only way to do that is to be able to rotate your apparatus and see that the fringes actually change. Okay, so being able to rotate is important. And so if you have a 10-meter apparatus and being able to keep it perfectly stationary, like all the parts perfectly stationary with respect to each other, and rotate it is, let's say, nigh impossible. You don't see LIGO rotating their apparatus. It's 4 kilometers long. So instead what they did is they built 2 of them with different orientations and at different locations on the Earth. So you can't do it like that. So they needed to make a bigger apparatus, but then they're limited by the fact that they can't maneuver an apparatus like that. They can't keep it stable against the noise. And so they added this feature to their system. They built their apparatus on a gigantic sandstone slab. So actually, if I go back to the beginning, this figure right here. So it's a big sandstone slab, okay? Because the heavier it is, the harder it is to shake. They have a light on one side, they have their beam splitter on the other, and then they have their 4 mirror arrays in the corners. And then they have their detector coming off of one of these as well. So this big sandstone slab, they want to isolate it vibrationally from everything. So they put it on this turntable. It's not actually a turntable. What it is, it's a table with a groove in it. So if you were to look at a cross section of it, it would look like this. Okay, and they filled this groove, so it's a circular groove. Of course, I drew that wrong. Please forgive the crudeness of this drawing. I didn't have time to do it to scale. They filled this groove with mercury. So they've got a liquid metal basically inside there, and then they float their tabletop with their interferometer on it. So here's their interferometer setup. They float this, probably has some kind of feet on it or something like that, in this mercury so that it stays perfectly level, and it's vibrationally largely isolated from the floor, and they can very, very smoothly rotate it. Because if it's on wheels or something like that, when the wheels jiggle, the wheels are going to cause the mirrors to shake. That's going to cause them to get slightly out of alignment, and that's going to mess up their measurement. Everything needs to be perfectly rigid as they make their series of measurements by rotating their turntable in order to basically find the direction of the wind. So it's floating on a vat of, or on a channel of mercury in order to allow for very smooth transitions from one position to another. So that's what this is. That's the mercury right there. Here's their table. That's their optical bench. Okay, so there's Einstein's equation. And this is how they made their apparatus bigger without actually making it bigger. Is they have their lamp right here. They have their detector over here. So the lamp comes in, hits this beam splitter, and they had to account for the behavior of the beam as it went through the beam splitter. Because in order to make their measurement as precise as they could. So light comes in, hits the beam splitter, splits into 2 directions. One of them comes along this direction, okay? And then the other one goes in this direction. And then those things on the corners, where is it? Right here. These things on the corners are a series of mirrors that are pointed in back towards the center. So that is a series of mirrors such that the light will bounce off of one, back and forth, 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 and then get recombined. Where does it recombine? So this looks like, oh, that looks like it's probably, this is probably their emitter. Okay, so here's their emitter, and it looks like this beam splitter is a little bit off. So they have 2 separate beam splitters, one where the beam is split in half and the other one where the beam gets recombined. So it looks like I'm not sure what this does. That looks like it's drawn in the wrong spot. So this looks like it's drawn in the wrong spot. Anyway, so where does this say? Oil lamp B. Oil lamp B. There's no B. Is that the oil lamp? Figure illustrates a folded light path used in the Michelson-Morley interferometer that enabled a path length of 11 meters. So basically, when you combine all these things together, that the light bounces back and forth between these different mirrors before it gets recombined, you get 11 meters in length. All right, so let's see. A is the light source. Okay, A is the light source and oil lamp. So that's A. A comes in here, and then they focus the beam, so that's why this lens. So ignore what I said over here. That was fake news. This is the real deal. Right here. So light comes in, hits this lens to focus it, to get it in the middle. Here's the beam splitter. So the beam splitter was right. C is a compensating plate so that both the reflected and transmitted beam, okay, so C, that's this. Doesn't look like a C, but that's what it is. So when I said before that they need to account for the fact that the light travels through one beam and reflects. So here's this, the beam splitter is a piece of glass, and the reflected beam doesn't pass through the glass, but the transmitted beam does pass through the glass, and so it's going to be shifted in wavelength a little bit. And so they add this second thing, the second piece of glass here. C is a compensating plate so that both the reflected and transmitted beam travel through the same amount of glass. Okay, and that's important since the experiments were run in white light, which I mentioned, so you can't just go with an integer number of wavelengths, you have to go with the total number of wavelengths. Extremely short coherence length, requiring precise optical matching. And I suspect that this C thing here was probably something that they could rotate and change the amount of glass that it went through. So you set everything up, you get a beam that goes through, make sure that everything is aligned, and then you can fix the alignment or fix the number of wavelengths correctly by probably rotating that piece of glass. We can maybe even look at the apparatus and see if we can see its ability to rotate. Doesn't really show up that way there, so never mind. If I were designing an experiment, that would probably be what I do, but of course I didn't do this experiment, so they had their reasons for what they did. But this is to compensate to make sure that the beams have exactly the right number of wavelengths in each arm. Okay, so the beam comes in, hits the beam splitter, splits in two directions, and bounces back and forth and back and forth and back and forth through these two different things, and then gets recombined at this beam splitter again, and comes in this direction. To their detector right here. So F must be the detector. F is a telescope right there. E is a fine adjustment mirror. Okay, so this is a fine adjustment mirror. Oh, okay. So here they have their apparatus set up, but they need to be able to adjust the arm lengths to make sure that they get exactly the right number of things. And so this E right here, which is basically the last reflection off of the path, so it comes down, hits D, bounces back and forth and back and forth and back and forth, and then they can adjust this one mirror. It has a little screw on the back. They can move it in and out in order to make sure that the lengths are exactly the same between the two things. Now, so the beam coming in this direction, the beam that transmits through the glass, how many times does it pass through glass? It goes through once here and then once there. So it goes through twice, goes through two pieces of glass, and then it reflects on the final pass. Okay, so it goes 1, 2, 3, and then reflects. And then the light that gets reflected off of this surface is going to go off of here and then back this way and goes through it twice more. So it reflects off the surface, goes through it twice. This one, the same. Anyways, the same idea. This is all to compensate for the path length. Okay, so that is how they set this up. So they can tune it, get exactly the kind of fringes that they want, and then they measure what is the difference in the speed of light between the two arms. So here is their interferometers. Basically, in this case, their interferometer is essentially set up like this, where they have the beam splitter there, and they have all these reflections that go on at the different corners. So the reflections come on, and it comes off, and then here's their detector, and they're checking to see. They start making measurements. They see their fringe. They see that in their case the dark line, and then they rotate the apparatus, looking through this telescope with their eyeball. So they're looking through the telescope with their eye and looking to see how much that fringe changes. If the fringe washes out, in which case they would say, we've seen the fringe wash out, and therefore we can see a difference in the speed of light in each of these two different paths, two 11-meter paths. And then they rotate it 90 degrees, and then they rotate it back in order to capture where is the ether drift, or where's the ether wind relative to our telescope. Then they can wait 12 hours. Now their instrument is on the opposite side of the Earth, moving in the opposite direction, and they can do exactly the same experiment again. They could do it 6 months apart, but why do it 6 months apart when you can do it 12 hours apart? Now the Earth is rotating, and they're moving in the opposite direction relative to the wind, so they make exactly the same set of measurements. And they determine how precisely can we measure the relative motion or the relative speed of light in these two different arms as it goes, or as we rotate this thing through a different angle. So they're looking for the maximum signal that they can find, and that is shown not here. That's the fringe pattern. That's shown right here. So the prediction is the dotted curve. That's what they would predict as they rotate through the luminiferous ether from the two different directions. And what they measured is the solid line. Solid line is what they measured, the drift in the fringes, and the dotted curve is what they predicted that they should measure. So the upper solid line is the observations at noon, lower solid line is for the evening observations. And so the apparatus has moved because the Earth is rotated, and so they get a new set of observations. The theoretical curves and the observed curves are not plotted to the same scale. The dotted curves, in fact, represent only 1/8 the theoretical displacement. Upper solid curve is for their observations at noon. Lower solid curve is aligned for the evening observations. The theoretical curves, that's this one, the dotted line, and the observed curves are not plotted at the same scale. The dotted curves, in fact, represent only 1/8 the theoretical displacement. So to actually plot this on the same scale, it would look like this. They would say, here is the curve that we predict from the theory, from the ether theory, and instead what we're measuring is something that looks like this. Okay, so that is what's shown here. These should be 8 times bigger. Those theoretical curves should be 8 times larger in amplitude. And then it has like north-south, east-west, north-south. So as they rotate through, they see no change. And that was the non-discovery of the luminiferous ether. So after they made these measurements, they basically said, there's no evidence for a luminiferous ether. There's no evidence that the speed of light changes in different directions because of this outside ether wind. So the model was that the wind is moving in some direction, the Earth is moving through it and rotating through it, and we should be able to see that by changing the orientation of our instrument, measuring the speed of light, the difference in the speed of light down these 2 different arms, and they didn't see it. It was their sensitivity to the fringes was good enough that they could say this doesn't exist. If the ether was there, we should have been able to see it by easily. Their data, their signal was 8 times bigger than the curve that's shown on this plot, and yet their noise is down here, like significantly smaller, like a factor of, it's probably like almost a factor of 10, like a factor of factor of 5 down here. So they would have been able to see it by a factor of 40. The signal that they saw was 40 times smaller than the prediction, which is pretty good. And so that basically showed that the ether didn't exist. And if the ether doesn't exist, then you have to change your theory. So now, this was a big deal because at the time, people thought light traveled as a wave through some medium. This eliminated that medium. And people had to really go back to think about what is the nature of light and how does light propagate through space. And so this was important for the development of Einstein's theory of special relativity, in that now he doesn't have an ether that he has to deal with. He's got to come up with, what is the nature of light in a vacuum, and how does it propagate, and how does that affect, people traveling relative to each other in this thing through space. Okay, it also was important for really understanding the equations from whatever that guy's name is, Maxwell's equations. So Maxwell's equations, they give you the speed of light, and it turns out that that's a fundamental constant. I'm not going to say nobody expected it, but this was not expected. They were expecting to actually measure the ether wind. And the fact that they didn't see it turned this into one of the most important experiments from the 1800s that really set the stage for modern physics. And these experiments have been done going forward since that time, because if you were to see a difference in the speed of light from 2 different directions, if you were to see an ether wind of any kind, then it would be a problem for special relativity. It would be a chink in the armor of Einstein saying, the speed of light is not constant in any reference frame. Instead, the speed of light changes depending upon your reference frame. And that, that's a big deal, right? That's a fundamental assumption of special relativity, is that the speed of light is constant in every reference frame. And in any transformation between those reference frames, the speed of light is still constant. And that would not be true here. And so any deviation from basically a non-detection would cause problems for Einstein's theory. So that was the measurements that were made in the Michelson-Morley experiment. The 1887 one, the 1881 one was from this design right here. The 1887 one, that's the big deal. That's the one that really did it. At Case Western Reserve University. So, and then the Wikipedia article goes through how you would interpret it based upon different reference frames and stuff. But that's a big deal. So starting here in Michelson-Morley in Cleveland, 1887, they were able to put an upper limit on the ether speed at 8 kilometers per second. So 8 kilometers per second, remember that light travels at 300,000 kilometers per second. So this is 8 out of 300,000. And so, they're able to exclude it to a really small number. So yeah, here again, the expected shift in the fringe was half a fringe, which would be easy to detect by eye, and they limit it to, they can do tests themselves, and as they're doing it, they measured a fringe less than 0.02. So there you go. There's their factor of 40. Basically their signal to noise was 40. So that's huge. More recent optical tests are better than this. So recent optical tests are like down at 10 to the minus 17 instead of 10 to the minus 1. Or 10 to the minus 2, I guess. So there you go. That is the Michelson-Morley experiment in all of its power and glory.